Section 250.52 of the National Electrical Code specifies the requirements for ground rings. The code states that the conductor shall encircle the building as near as practicable at every floor level and at the attic and basement whenever present. At corners, the conductor shall be bent around the corner and extend at least 6 inches or 152 millimeters on each side of the corner. This requirement clearly indicates that the ground ring conductor must encompass the entire perimeter of the building at each designated level. This includes every floor, the attic, and the basement if a basement exists. The interpretation suggesting that only 20 feet of wire is sufficient for creating a ground ring is incorrect. The ground ring's purpose is to establish a continuous and reliable pathway for ground fault currents, facilitating their return to the grounding electrode system. A mere 20-foot length of wire would be inadequate to fulfill this function, particularly in the context of larger buildings. Furthermore, the code stipulates that a minimum of 20 feet of the ground ring conductor must be bare. This requirement is crucial because the bare portion of the conductor is intended to directly contact the earth, enabling the dissipation of ground fault currents into the surrounding soil. Therefore, the proper understanding of Section 250.52 is that the ground ring conductor must completely encircle the building at all specified levels, including each floor, the attic, and the basement. Additionally, at least 20 feet of the conductor must be uninsulated, meaning it must be bare to facilitate effective grounding. In simpler terms, imagine a building. The ground ring is like a belt that goes all the way around the building at different levels, such as the base, each floor, the attic, and the basement, if there is one. It's not just a small piece of wire. At least 20 feet of this belt needs to be bare, meaning without insulation, so it can touch the earth and help with electrical safety. The code insists on this full encirclement to ensure that any fault current, which is an unintended electrical current, has a reliable path to the ground. This helps to protect the building and its occupants from electrical hazards. The 6-inch or 152 millimeter extension requirement at corners is there to maintain the continuity and effectiveness of the ground ring. It ensures that the grounding path is not compromised at the building's corners, which are often points of stress and potential discontinuity in the electrical system. It's also important to consider the practical implications of installing a ground ring. The conductor should be as close to the building as possible, but it should also be protected from physical damage. The depth at which the conductor is buried can vary depending on local soil conditions and the specific requirements of the electrical system. However, it should be deep enough to provide good contact with the earth and to prevent the conductor from being easily disturbed. When installing the ground ring, it's essential to use proper connectors and grounding techniques. All connections should be made securely and protected from corrosion. The grounding electrode system should also be inspected regularly to ensure that it is in good condition. The purpose of the ground ring is to provide a low impedance path for fault currents to flow back to the source. This helps to trip circuit breakers or fuses, which interrupts the flow of electricity and prevents electrical shock. A properly installed ground ring can also help to reduce the risk of fire caused by electrical faults. The ground ring is a critical component of the electrical safety system, and it should be installed and maintained by qualified electricians. Now let's delve a little deeper into the specifics of NEC Section 250.52. This section is not just about the length and placement of the ground ring conductor. It's also about ensuring that the ground ring is effectively connected to the grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. These electrodes are connected to the ground ring conductor, providing a path for fault currents to flow to the earth. The NEC specifies the minimum size of the grounding electrode conductor, which is the conductor that connects the ground ring to the grounding electrode system. The size of the grounding electrode conductor is based on the size of the service entrance conductors, which are the conductors that bring electricity into the building. It's crucial to select the correct size of grounding electrode conductor to ensure that it can safely carry the maximum fault current that is likely to occur. The NEC also specifies the methods for connecting the ground ring conductor to the grounding electrode system. These connections must be made using approved connectors and techniques. The connections must be mechanically sound and electrically conductive to ensure that they can withstand the stresses of a fault current. In addition to the requirements for the ground ring conductor and the grounding electrode system, the NEC also includes requirements for the grounding of metal enclosures and equipment. Metal enclosures and equipment that are likely to become energized must be grounded to prevent electrical shock. This grounding is typically achieved by connecting the metal enclosure or equipment to the ground ring conductor or to the grounding electrode system. The NEC specifies the methods for grounding metal enclosures and equipment. These methods include using grounding conductors, bonding jumpers, and other approved techniques. The grounding connections must be made securely and effectively to ensure that they can safely carry fault currents. The proper installation and maintenance of grounding systems are essential for electrical safety. Grounding systems protect people from electrical shock, reduce the risk of fire, and help to ensure the reliable operation of electrical equipment. Electrical inspectors play a vital role in enforcing the NEC requirements for grounding systems. Electrical inspectors review the design and installation of grounding systems to ensure that they comply with the NEC. They also inspect existing grounding systems to identify any potential hazards. The requirements outlined in NEC Section 250.52 are intended to create a safe electrical environment within and around a building. It's not just about meeting the minimum requirements of the code, it's about ensuring that the grounding system is effective and reliable. To further clarify the intent of Section 250.52, let's consider some examples. Imagine a rectangular building with 4 corners. The ground ring conductor must run along the perimeter of the building, passing each of the 4 corners. At each corner, the conductor must be bent around the corner and extended at least 6 inches or 152 millimeters on each side of the corner. This ensures that the ground ring forms a continuous loop around the building. Now imagine a building with multiple floors. The ground ring conductor must be installed at each floor level, as well as in the attic and basement if present. This creates a network of ground rings that are interconnected and provide multiple paths for fault currents to flow to the grounding electrode system. This redundancy helps to ensure that the grounding system is effective even if one of the ground rings is damaged. The specific installation methods for ground rings can vary depending on the building's construction and the local soil conditions. In some cases, the ground ring conductor may be buried directly in the earth. In other cases, it may be installed in a trench or conduit. The NEC does not specify the exact depth at which the ground ring conductor must be buried, but it should be deep enough to provide good contact with the earth and to protect the conductor from physical damage. The selection of the correct size and type of ground ring conductor is also important. The conductor must be sized to carry the maximum fault current that is likely to occur. It must also be resistant to corrosion and other environmental factors. Copper conductors are commonly used for ground rings because they are highly conductive and resistant to corrosion. However, other materials, such as aluminum, may also be used in some cases. The NEC provides guidance on the selection of appropriate conductors for grounding system. In addition to the requirements for the ground ring conductor itself, the NEC also includes requirements for the connections to the ground ring. All connections must be made using approved connectors and techniques. The connections must be mechanically sound and electrically conductive to ensure that they can withstand the stresses of a fault current. The use of improper connectors or techniques can compromise the effectiveness of the grounding system and create a safety hazard. Proper grounding is not just a matter of following the NEC requirements. It's also a matter of understanding the principles of grounding and the importance of creating a safe electrical environment. Grounding is a fundamental aspect of electrical safety, and it should be given the attention it deserves. Now, let's consider the scenario where a building has an addition. Does the ground ring need to be extended to encompass the addition? The answer is typically yes. The ground ring should encircle the entire building, including any additions, to provide a continuous path for fault currents. The ground ring conductor should be extended to the addition and connected to the existing ground ring conductor using approved connectors. The connection should be made in a way that maintains the continuity and effectiveness of the grounding system. The installation of a ground ring may also be required when a building undergoes significant renovations or alterations. If the renovations or alterations affect the electrical system, it may be necessary to upgrade the grounding system to meet the current NEC requirements. This may involve installing a new ground ring or modifying the existing ground ring. The decision to install or modify a ground ring should be made in consultation with a qualified electrician or electrical engineer. They can assess the specific needs of the building and recommend the appropriate grounding solutions. In some cases, it may be necessary to perform a ground impedance test to verify the effectiveness of the grounding system. A ground impedance test measures the resistance between the grounding electrode system and the earth. A low impedance is desirable because it indicates that fault currents can flow easily to the earth. If the ground impedance is too high, it may be necessary to improve the grounding system by adding additional grounding electrodes or modifying the existing grounding electrodes. The NEC provides guidance on the acceptable limits for ground impedance. The maintenance of a ground ring is also important. The ground ring should be inspected regularly to ensure that it is in good condition. Any damaged or corroded conductors or connectors should be replaced immediately. The grounding electrode system should also be inspected to ensure that it is still effective. The soil around the grounding electrode should be kept moist to improve the conductivity of the earth. In dry climates, it may be necessary to water the soil around the grounding electrodes periodically. The effectiveness of a ground ring can be affected by a number of factors, including the soil conditions, the depth of the conductor, and the quality of the connections. Soil conditions can vary widely depending on the location. Some soils are highly conductive, while others are not. The depth of the conductor can also affect its effectiveness. A deeper conductor is more likely to be in contact with moist soil, which improves its conductivity. The quality of the connections is also critical. Poor connections can increase the resistance of the grounding system and reduce its effectiveness. Therefore, it's important to ensure that all connections are made properly and that they are protected from corrosion. The NEC is constantly evolving to keep pace with changes in technology and electrical safety practices. It's important for electricians and electrical engineers to stay up to date on the latest NEC requirements. The NEC is published every 3 years, and it's essential to review the latest edition to ensure compliance. The NEC is not just a set of rules, it's a comprehensive guide to electrical safety. By following the NEC requirements, electricians and electrical engineers can help to protect people from electrical shock and reduce the risk of fire. Proper grounding is an essential component of electrical safety. The proper interpretation of NEC Section 250.52 is critical for ensuring that ground rings are installed correctly and that they provide effective grounding for buildings. Remember, the ground ring must encircle the entire building at every floor level, attic, and basement. Also remember that at least 20 feet of the conductor needs to be bare to allow for ground fault current dissipation.